So just give me some 2 minutes. I'm trying to join the meet through my iPad. I think there is some issue. So in today's lecture, there's a good chance that there will be a lot of hiccups because I am recording or I am taking this lecture from my village actually, and my village doesn't have a good internet connectivity. Uh, so there's a good chance that there will be a lot of voice breaks and you know uh, a lot of disturbances. Uh, However, I am recording it through an offline software, because of which the recording will be clean. That much I can assure. However, I cannot guarantee that today's lecture will be without any hiccups. There's a good chance there will be a lot of disturbances today. Just give me 2 minutes to just join through this thing. By the way, is my voice audible? Can someone just write it in chat or just unmute themselves or tell me? I'm not. Okay. Yeah, I mean, yeah. So yeah, not sure. Yeah, this session could be a bit tricky today. So yeah, cannot guarantee that there will be no there will be absolute clarity. So I'm sorry for this, but yeah, yes, we'll have to manage it somehow today. Okay. Okay. So I think I have joined through this thing. Okay, let me share my screen. Okay. Just create another notebook. I will switch to this iPad recording. Okay. So this is clear. So I hope the screen is visible. I will just start. So there's again good chance that there will be a lot of lag between what I write and what I speak. Uh, so yeah, I'm sorry for today, but the recording will be that much I can assure that the recording will be very clear. And yeah, so please bear with this today, and we'll make sure that this doesn't happen from next time. Okay, so this is like week four. Today we will be discussing week four stuff. So week four is basically about special distributions. Special distributions, where in a nutshell we will we saw a lot of new distributions and properties of such distributions and stuff like that. Uh, so the questions or the problems that we will be solving today will be based on these special distribution itself. In particular, we'll be seeing applications of these distributions, and how these distributions are used to basically model uh, different scenarios or different use basically the use cases of these different distributions. Okay, so maybe we can straight away get started, right? So let's start with the first question. So the first question is that, so let's say x is a random variable. X is a random variable. However, it is the PDF. It has a PDF, so it has a probability density function, right? This is symmetric. What do we mean by that? So let's say if fx of x is the distribution of uh, is the distribution function of is the PDF of the random variable x, then about x we know that fx of uh, fx of minus x is equal to fx of x. This much we know. So the question, so we are given four statements and we are asked which of them is correct, right? So let's look at them. So the first option is expected value of x is equal to 0. The second option is x and minus x have have same distribution. The third option is x and 1 minus x have same distribution. The last option is expected value of x always exists. So these are the four statements. Uh, so let's look at them one by one. So actually the A and D, uh, these two are sort of related because they are talking about the expected value of x, right? So let us look at the expected value of x. So what will be the expected value of x? Expected value of x by definition is the integral minus infinity to infinity x f of x, right? Dx. This is the definition of expected value, right? However, now we can split this integral into two parts, right? First will be minus infinity to 0 x f of x dx plus integral 0 to infinity x f of x dx, right? Now this will be equal to, so let's write this term first, the second term first. This will become integral 0 to infinity x f of x dx. Now in the second term, so like for the integral where the limit goes from minus infinity to 0, what we can do is we can actually change the variable from x to minus x, right? So what will that become? If you change the variable from x to minus x, the limits will change, right? Because if x is going from minus infinity to 0, what will minus x go from? Minus x will go from 0 to infinity, right? Because it's like you are looking at the left part of the x-axis. However, if you look at minus x, it will be the right part of the x-axis. So this will become again 0 to infinity. X will become minus x. So f of minus x dx, right? However, and this will come with a minus sign outside. You can just this is a simple change of variables in integration, right? So like what I'm saying here is, look at a new variable y which is equal to minus x. You will see that dy is equal to minus dx. So d uh, right, and so you will like substitute it here in the integration, and then like do this stuff again. And I mean, this is a basic elementary stuff basically. I don't know if it's clear, but yeah, it's a you just need to do a change of variable, that's all. And now since we know that f of minus x is equal to f of x, since we know that this is equal to f of x because it is given to us, right? This will become integral 0 to infinity x f of x dx minus integral 0 to infinity x f of x dx, right? And now since these two things are exactly the same, this will just cancel out and this will be equal to 0. So expected value of x is equal to 0, right? Now, so this looks very good, right? I mean, if you look at this calculation, it is very tempting to think that the first option here is correct. However, this is only true when expected value of x exists. What if expected value of x doesn't exist? So, I mean, in the lectures, you must have seen something called Cauchy distribution, right? Cauchy distribution, where f of x is equal to 1 over 1 plus x square. Uh, in this case, basically, what happens is uh, your expected value of x, it doesn't exist. Doesn't exist. This thing doesn't exist. I mean, you can go back to the lectures and see, because why does this doesn't exist? You will see that the integrals have a definition, and so basically integrals are nothing but an infinite summation. And if that infinite summation has a limit, only then the expectation exists, otherwise it doesn't. And in the case of Cauchy distribution, that limit doesn't exist. So, so in this case, though the distribution is symmetric about x about the origin, about the y-axis, however the expectation doesn't exist. Hence you cannot say that expected value of x in this case is 0. So so actually this statement is not correct. The first statement that you saw here is not correct. Expected value of x is equal to 0 only if the expectation exists. That is the fully correct statement. However, if the expectation doesn't exist, you cannot say that expected value is 0. So there should be another remark here. It is true only if expectation, only if expectation exists. If the expectation doesn't exist, then it's not, you cannot say that it is equal to 0 because it doesn't exist, right? And hence, similarly, the D option is also not correct because expected value of x need not exist always, right? As you can see a you can just give a counter example, which is the Cauchy distribution, right? Now let's look at the B option here. X and x have same distribution. So, okay, let's see. So what is the probability? So whenever you have to find the density of a new random variable derived from some old random variable, you look at the CDF of the random variable, right? The distribution function. So what is the probability that capital, I'm looking at minus x now, minus x is less than equal to some small x, right? Whenever, I mean, you must have seen this kind of calculations by now. This is equal to probability that x is greater than or equal to minus x, right? What is the probability that x is greater than or equal to minus x? Now let us look at this random variable whose CDF is like this. It's a, sorry, It's a symmetric thing about the origin, about the y-axis, right? Now we are asking what is the probability that this x is greater than equal to some minus x, which is here. Let's say minus x will be here. So all this entire area, this thing is basically your so this area under this curve will tell you the probability that x is greater than or equal to some minus x, right? Now what is this probability equal to? Well, uh, I mean, you can see that this thing is, since because this is symmetric, right? Because of the symmetricity of, because the symmetric nature of this curve, you can see that this thing is exact, this area will be exactly equal to, you know, the same things, the same, sorry, uh, maybe I need to make it a little bit, just give me some time. So let us look at, so this curve, the area, this area that I have shaded in this region, this shaded region in this thing, is exactly equal to this area, right? It is just that in this case we are looking at the left side of the curve, right? This in this case it is going from minus x to infinity, and look, we are looking at the area under that region. In this case, we are looking at the left side of the curve where it is going from x to minus infinity, and we are looking at the area under that part of the curve. Essentially, the areas are same, right? Because of the simple symmetric nature of this curve. So we can write this thing as probability of x less than or equal to small x. This we can do. I mean, I will just write it down, this thing by symmetry, you know. And we know that this thing, that probability of capital X small or less than equal to less than or equal to small x, this is nothing but uh, this f, the CDF fx of x, and the LHS was f minus x of x, right? So from here we can conclude that f minus x of x is equal to f capital X of x, and hence they have same CDF, and if they have same CDF they will have same PDF as well, because PDF is just the you know, differentiation of the CDF with respect to x. So I mean, by this thing we can conclude that, you know, x and minus x will have the same distribution, and hence this option, this B option, is actually correct. However, the same thing won't hold for you know, the C option. For let's say, uh, so what is the probability that 1 minus x is less than or equal to some small x? This thing will be equal to probability of x greater than or equal to 1 minus x, right? Now this thing is not, this is basically not equal to probability of ca capital X less than or equal to small x, right? This is actually, this thing is actually equal to probability of x. You're looking at 1 minus x, right? Uh, so you are looking at minus x and one step ahead of. So this is actually equal to, less than equal to, you can write it as x minus 1, and this is equal to fx of x minus 1, whereas this is f of 1 minus x or of x. So you can see here that, you know, the two random variables 1 minus x and x, they don't have the same CDF. If they don't have the same CDF, they cannot have the same PDF as well. So from here you can say that the C option here, that is also incorrect. right? uh, I know that today, I mean, there is a possibility that you might not be hearing my voice correctly, or there will be a lot of disturbances. But please, I'm sorry for this. But yeah, you can look at the recording. The recording will be very clear. That much I can assure. And this will happen only this time. From next time, I will again make sure that there will be no disturbances and everything will be pretty much fine. Okay. So let us look at some other problem. So here is another problem. The second problem. So now here is a question, right? The question is, so we are given two nodes A and B. Node A and there is another node B. Okay. And these two nodes are connected in parallel with some components. And these components have some reliability. Basically it tells you the probability by which these components won't fail. So this component won't fail with probability 0.95. This component won't fail with probability 0.9. This thing won't fail by the probability 0.92. Similarly, this component won't fail with the probability of 0.85. This component has a reliability of 0.95. The question is, what is the reliability reliability of the complete system? So basically, what is the probability that entire system won't fail? That is the that is the thing, that is the quantity that you're asked to calculate. So basically, probability of not failure failure is equal to what? It is equal to the 1 minus probability of failure, right? Because failure and not failure are like complements of each other. So you can say that the probability of not failure is equal to the 1 minus probability of failure, right? Now, so let's call these components C1, C2, C3, C4, C5. So what is the probability of failure now? So the failure can happen, you know uh, so if you want the failure to happen, then either one of these things can fail, or I mean both of these things should fail, right? I mean, see, the first one should also fail and the second one should also fail. Only then you can say that uh, basically the entire thing fails, right? So that will be equal to 1 minus. So what is the probability that this first line? So what is the probability that this first line that is here, what is the probability that uh, that line fails? That will be simply equal to, so if you want, if so these are the probabilities that they will not fail, right? So again, so let me, okay, maybe I will write it like this, right? Probability of failure, which is equal to probability of failure of line 1, which is the first line. Let me call this line 1 and this is line 2, into probability of failure of line 2. That is equal to 1 minus, what is the probability of failure of line 1? So 1 minus probability of, this is not failure of L1, into 1 minus probability of not failure of L2. Now, what is this thing? 1 minus probability of not failure. Now, if you want all of them to be working correctly, you can just multiply the reliability of each of the components. So just multiply 0.95 times 0.90 into 0.92, right? This thing into 1 minus, what will this be? 0.85 times 0.95. 0.85 times 0.95. Now, so basically you have to come up till this thing to, I mean, now you can simply use your calculators to, uh, do this, to do this calculation, and it will turn out to be 0.9589, this thing. So again, a pretty straightforward thing. I mean, there's nothing special about this thing. Uh, it's just you have to just, this is a simple kind of an elementary school thing, but yeah, uh, yeah, it's quite simple, yeah. Uh, then I think we can look at some other question. So let me know if there is something is not clear, right? I mean, I am trying my best to, explain it in full detail, but it's possible that something is not understandable or comprehensible. In that case, please let me know. Okay. So, okay, okay, uh, so here is another question, third question. Okay. So there is a page. So there is a printed page. Okay. Each page has 2000 positions. You can think of it as 2000 positions where a word can go in. Okay. The typist, so someone is typing on this page, and the typist, he makes one error uh, at in every 4000 positions, right? So first of all, how many errors can he make two in one page? So if there is one error in 4000 positions, how much error will he make in 2000 positions? This is equal to 1 by 2. So this is like the rate, right? Or in other word, errors per page, or in this is also, let's call this lambda. So okay, so lambda is given to be half. Okay, this is like the rate of error, the how much error he can make per page, that is given to be half. Okay, now it is given to us that uh, the number of errors per page, this is a random variable, right? This is Poisson distribution, this is distributed as Poisson with some rate lambda, right, which is given to us by 1 by 2, right? The question is, what is the probability that the number of errors on a page is equal to 0? This is the question. So maybe I will repeat the question. So there is a page. So someone is writing a book, let's say, and at on each page there are 2000 positions. Okay, 2000 words, let's say. There's a typist. The typist makes one error in every 4000 position. That is his rate of doing mistake. From this, we can calculate how much error he will make on each page, right? If he makes one error in 4000 position and there are 2000 position on one page, he will make 1 by 4000 into 2000 errors per page, which is equal to 1 by half, 1 by 2, right? Now 1 by, so this is basically the rate at which he makes an error per page. This was the rate of error at which he makes an error per position. This is the rate of error in which he makes per page, which is one half. So that is what we are calling as lambda. Okay, so lambda is given to be half. Now it is also given to us that the number of errors per page, this random variable, so number of errors that are going to happen on a particular page is a random variable, right? Because it is there is some stochasticity by which it is happening because of this typist. So this number of errors per page is distributed as Poisson lambda, right? It is a Poisson random variable with rate lambda, and lambda is given to be half. The question that is asked to us is what is the probability that when the typist types on the paper, he will make no error, that the number of error is equal to zero. What is that probability? So this is simple. So probability of number of errors is equal to k. What is this probability? Since we know that this is Poisson distributed, it is equal to lambda raised to k, right? E raised to minus lambda by lambda fact by k factorial, right? By k factorial. This is the distribution, right? I hope this is right. As far as I remember, this is correct, right? So now k is equal to 0. So just put k equal to 0. Number of errors is equal to 0. This thing is equal to lambda raised to 0, e raised to minus lambda by 0 factorial. 0 factorial is equal to 1, right? So lambda raised to 0 is 1, e raised to minus lambda by 1. So this is e raised to minus lambda. Now lambda is given to be half, right? Here. So this is equal to e raised to minus 1 by 2 or e raised to minus 0.5, whatever. You can calculate this thing by your calculator, but yeah, this is where you should be able to come. So yeah, again a simple thing, like a question on basically Poisson distribution. Nothing very fancy about it. I mean, it's quite straightforward. The only trick is to understand what is given to you. So you have to basically understand that lambda is the rate here, and you have to calculate the rate. Okay. So let us look at like similarly another question. So these are simple questions, right? It's just about you just need to know the properties of these new random variables, these special distributions. If you know that much, it's enough. Okay. Okay. Then let us look at some other question. The fourth question. Which question should I take? Uh, Sorry, can you? Uh, yeah, I haven't changed it. I am still on the same page. That's why. Oh, I see. Okay. Oh, now I understand what you are saying. Oh, I see. So it hasn't changed at all from. So the last thing that you are, what is the last thing that you're able to see on the screen? Is it P of number of errors equal to 0? Is that what you're saying? Can someone tell me like till what point you are able to see? I think I think there's some network issue again because of which we are not able to see anything. Yeah, this cannot be helped actually. Cannot do anything about this. Maybe I can stop presenting and then restart presenting. Okay, I have stopped broadcasting. We'll start broadcasting again. Maybe I'll rejoin from. Okay. Oh, sorry. Okay, I have joined again. Is the screen visible now, or is it still not visible? Is the screen visible now, or is it still not visible? Hmm, okay. So I have stopped broadcasting. I'm resharing it. Is it visible now? Maybe. Hello, is it visible now? Today. Hello, so is my voice audible? Okay, so maybe I'll just continue because I think the internet issue can't be resolved at this point, and you cannot do anything about this thing. So maybe you can just look at the recording afterwards. I think that is the only solution that I have right now. Cannot do anything else. Uh, so yeah, maybe I'll just continue. Nonetheless. So yeah, I'm sorry, but yeah, I will just continue, and you guys can have a look at these lectures afterwards on YouTube. I'll just write it on the chat. Uh, I'm sorry. Okay, so I will just continue. So there are two. So the next question basically tells us that there are two manufacturing plant R and S. Okay, and so both of them manufacture bulbs, and if X denotes the uh, number of, basically tells X is basically the time to failure in months of a light bulb. Uh, so given this, the bulbs that are produced from so probability of basically X, given that it is coming from the manufacturing plant R, this is actually an exponential distribution with your with parameter 4, right? And similarly, probability of X, given that it is coming from the other plant S, this is exponentially distributed with parameter 2. Okay. Also, it is given that plant plant R uh, produces three times bulbs uh, as plant S. This is also given to us. And basically, a company gets the bulbs from both of these plants, and it mixes all the bulbs. So, what is the probability that, given that you randomly pick a bulb from this uh, randomly pick a bulb from this lot of randomly mixed bulb, what is the probability that X is greater than 4? This is the question that is asked. So what is given to us? Which is so let us call LR as uh, so let us call LR as bulb produced by R, and similar LS is a bulb produced by S. Okay, we know we are given that P of LR is equal to 3 times P of LS. But we also know that P of LR plus P of LS, this is equal to 1, which tells us that 4 times P of LS is equal to 1. This tells that P of LS is equal to 1 by 4. This tells us that P of LR is 3 by 4, right? This is given to us. We are also given that x given LR is exponential 4 and x given LS is exponential 2. Now we are asked what is the probability of x is greater than 4. So now what we will do is we will use this so probability of x greater than 4 is equal to P of x greater than 4 uh, LR plus P of x greater than 4 LS. So basically we are partitioning this event x greater than 4 into two disjoint partition LR and LS. Now so now we will use basically our simple Bayes rule. This is equal to P of x given 4 given LR into P of LR plus P of x greater than 4 given LS into P of LS. So basically we are now simply decomposing each of the probabilities into things that we know, that we are aware of, right? Uh, so this thing, we know that this thing is actually exponentially distributed, and for an exponential distribution the probability of x get greater than some small x is equal to e raised to minus x by lambda, right? So this will be equal to minus 4 by 4 into P of LR. This thing is 3 by 4. Similarly this thing will be e raised to minus 4 by 2 because the rate here is 2 into uh, 1 by 4, right? This will be the probability, and now you can just simply use your calculators to calculate this probability. Okay, so a simple thing, just that you have to basically break things down into the terms that you can calculate, or what it is, right? Now uh, so let us look at some other question. So this was the fourth question, right? Let us see how many questions we are able to do today. Okay, so the fifth question, uh, let us look at it. Okay, so let us see. So you are given a distribution f of x, which is equal to k e raised to minus mod x minus 2 by 2 and minus infinity x less than infinity. This is given to you. So the question is, what is the value of k? Uh, so what is the value of k is the question, right? So it's actually a simple question. You just have to, do simple probability, like simple integration. So again, whenever you are asked the value of some, unknown variable, just use this fact that f of x integral f of x dx minus infinity to infinity, this is equal to 1. Okay. Uh, if this is equal to 1, this means that 1 is equal to integral k e raised to minus mod x minus 2 by 2 dx minus infinity to infinity. Now break this into two terms where you will get rid of this mod thing. This is equal to, so first will be minus infinity to 2 where x is less than 2. In that case the mod will break as 2 minus x minus 2 minus x by 2 dx plus integral 2 to infinity k e raised to minus x minus 2 by 2 dx, right? Now what will this become? This will become minus infinity to 2k e raised to x minus 2 by 2 dx plus integral 2 to infinity k e raised to 2 minus x by 2 dx. Okay, this will become what? So now what is this integration equal to? So k is a constant in all of it, so that will simply come out. In the first term, this integral will be e raised to x minus 2 by 2, uh, so plus x minus 2. However, there is a 1 by 2 there, so that will come out here because x is multiplied by half there. Similarly, this thing will become uh, e raised to 2 minus x by 2, and there will be a minus 1 by 2 thing, 2, and there will be a minus 1 here, which will come out, and the range for this thing will be minus infinity to 2, and range for this thing will be 2 to infinity. Now just doing simple calculation, right? So this will become what? So uh, so if you put x equal to 2 here, this will become 2 minus 2 0 by 2, so this will become 1 minus, if you put minus infinity there, e raised to minus infinity is again 0, this will become 0 by 2, right? That is the first term minus. So what will this thing become? If you put infinity here, e raised to again 2 minus infinity will be like e raised to minus infinity, which will be equal to 0 minus. If you put 2 there, it will become 2 minus 2 0. So e raised to 0 is 1 by 2, right? So 1 by 2 minus of minus 1 by 2, that will become uh, uh, that will become 1 by 2 plus 1 by 2, which is 1. So this will become k. 1 is equal to k. So this is what you get. Maybe just do a cross check if I have done some mistake, but yeah, it looks like this is the correct answer, right? Yeah. So okay, so the question was that this is a given distribution, okay? Distribution, this is a given PDF. The question is, what is the value of k? You have to find the value of k. Okay, so whenever you are given such question where you have to find value of some scalar unknown, the only thing that you need to do is you use the this following identity, that integral of f of x dx minus infinity to infinity is equal to 1, right? Because the integration of a PDF from minus infinity to infinity should be equal to 1. So we are just using that thing, right? And this the limit of this integral, you can split this integral into two parts. The first part where this thing will be positive, and the other part where it will be negative. So if x is between minus infinity to 2, so when x is less than 2, mod of x minus 2 will be equal to 2 minus x, right? Because the mod will uh, come out to be negative. So for example, mod of 1 minus 2, this is equal to mod of minus 1, which is equal to 1, which is equal to mod of 2 minus 1. So sorry, which is equal to, which is just equal to what? 2 minus 1, which is equal to 1, right? So I'm just using that thing here. So if you split it from minus infinity to 2, it will be 2 minus x by 2 dx. And the second part of this limit will be from 2 to infinity. And in that case, the mod will split just as x minus 2. Is that clear? Hello? Okay. So I'm just using that, and then after that we are just basically doing integration. So minus infinity to 2 integral of this thing. So x integral e raised to x is just e raised to x, right? So e raised to x minus 2 by 2 will be x e raised to x minus 2 by 2. However, there is a 1 by 2 factor that will come out, right? That is what I am writing here. Uh, Similarly, this thing, I mean, just simple calculation and you will get this answer. So you just need to calculate, like split the integral appropriately, and the rest of the things are easy. Uh, Let us look at some another interesting question. Sixth question. So the question here is that x is chosen uniformly from uniform 0 1. So x is a random variable which is chosen randomly from the interval 0 comma 1. Okay. So what is the probability that first first decimal digit of x is equal to 3? Okay. So here is this interval. This is 0, this is 1. Whenever you pick any point at random from this, so let it will be something like 0.12, right? Or it can be like uh, it can be 0.24, it can be 0.378, something like this, right? It will be a decimal, it will be a basically a fraction, right, between 0 and 1. The question is, so let us say that the fraction is like 0 x, y, z, a, b, c, d, and so on. So if this is the decimal, if this is the number that you are, you have picked, what is the probability that x is equal to 3? What is this probability? So, I mean, this is actually a very common sense question. Actually, it is a logical question. So when can this thing be 3? When is it possible that that the number I choose is like 0.3 and then some x, y, z, something, blah, blah, blah. If this is 0, this is 1. It is only possible when, so this is like 0.1, this is 0.2, this is 0.3, right? This is 0.4, this is 0.5. If I choose a number between 0.1 and 0.2, is it possible that the first decimal digit is equal to 3? X equal to 3, is it possible? It's not possible because any number between 0.1 and 0.2 will be of the form 0.123 or 0.178, something like this. Any number between 0.2 and 0.3 will be of the form 0.2x, something like this, right? Similarly, any number between 0.3 and 0.4, this number will be like 0.3 some xyz. Okay. So basically, if you want the first decimal digit to be equal to 3, the number has to come, the number that you are going to pick has to come between has to come between 0.3 and 0.4. Only then the first decimal digit will be equal to 3. So in other words, what this thing translates to is the probability of 0.3 0.3 x greater than equal to 0.3 and less than 0.4. This is the probability that is being asked to you. So if x is a uniform random variable, what is the probability that it is between 0.3 and 0.4? Only then the first decimal digit will be equal to 3. Now this thing is equal to what? You know how to calculate probabilities by now. It's integral 0.3 to 0.4 fx of x dx, right? So what is this? 0.3 to 0.4, and this is just 1, right? 1 dx, because it's a uniform random variable between 0 and 1, so f of x will be 1. So now this will become what? This will be x from 0.3 to 0.4. This will be 0.4 minus 0.3, which is equal to 0.1, which is equal to 1 by 10. This is the answer. Uh, yeah, let me know if it is clear or if you have any doubts. Right, so uh, maybe I will solve just one last question and then we can stop because anyway there's a lot of hiccups that are happening today. So I won't solve a lot of question. I'll just one last question and then we will stop. Okay. Uh, okay. So the question is, let's say x1, x2, so on till x2n. They are IID 0 uniform 0 1 random variables. Okay. So there are 2n random variables. Each of them are independent and identically distributed, and they are distributed with this PDF uniform 0 1. And let's say that x of r, this denotes rth largest among x1 till x2n. So rth largest number between amongst all these is denoted by x sub bracket r, right? So do you know? So the question basically is, what is the distribution of x of r? This is something that was taught in class actually. So you have to just use a simple property of, this is uh, so this is called sufficient statistics, if I am not wrong. The so x of so in this case, whenever x1, x2, x3 these are IID distributed, so you need to remember the property that x of r is actually distributed as beta distribution with parameters r, comma n minus r plus 1, where x of r is the rth largest in x1 till xn. However, here we are given x2n. So in this case, in our case, x of r will be distributed as beta r comma 2n minus r plus 1. So if you know this, you can actually answer a lot of things. What is the distribution of x of 1? This will be distributed as beta. So r is equal to 1 here. So 1 comma 2n minus 1 plus 1, which is equal. So this is actually beta 1 comma 2n, right? Similarly, x of, let's say, what is the distribution of x of 2n? That will be distributed as beta 2n comma 2n minus 2n plus 1. This is actually beta 2n comma 1, right? So this is, so you can simply answer stuff like this easily, right? What is x of n? So what is the distribution of the median? That will be actually beta n comma 2n minus n plus 1. This is actually beta n comma n plus 1. So yeah, just using the property that, rth largest value, if your random variables are distributed IID uniform 0 1, it follows beta distribution. Simple simple stuff. All right, so I think we will stop here. I know it was a rather short session because of, some network issues at my end. However, from next time I will make sure that these things doesn't happen. Today I cannot help it, otherwise I would have done something. But yeah, really sorry for this. But yeah, I mean, from next time I will make sure that these things doesn't happen. Okay. So maybe thank you for then joining and see you next time. Okay. Uh, okay. Let's end this session. Thank you for joining. Bye. I will just disconnect my iPad first. And I will just leave this. Stop recording.